welcome to this tech session. My name is Mike Lovell. Some of you may know me from previous presentations here at Openwest on topics like IPv6 or OpenWRT or QEMU or OpenStack. I've done a number of them over the years. So there is some contact info for me. And I did just upload this slide deck to the web server right there, and it has some of my other talks as well if you guys are interested in those. So, a little bit of background information on me. I'm a long-time tech geek. Done a number of things over the years. Right now I am just a server and network administrator for a small company of about 80 people, 85 I think is where we're at the moment. I guess from a on-paper perspective, the big thing was I was the senior system admin for the storage system at Mosey, which when I left was like 70 petabytes. So there's a little bit of bragging rights that fit nice on paper. So, why should I guess you guys care about how a Linux system boots? Well, there's a number of reasons. One of the big ones, for at least given the time frame of where we are right now and recent events in the overall computing community, that's two tough words to say next to each other, there have been a lot of changes that have been happening. We've kind of been throwing off some of the shackles of old antiquated systems and building new replacements. And so this affects how a Linux system boots. And it's somewhat interesting and important to understand what those changes are and how they affect things and some of the reasons that went into the decisions that were made. Another thing is, crap happens, things break. It's important to know what's going on in a normal situation so that when things break, you can go through and fix them. I'm guessing if anyone has tried to dual boot Windows and Linux, they've gotten to a point where they can't boot one or the other. So by understanding how, at least on the Linux side, things works, you can hopefully fix at least the Linux side. Also, once you understand the basics of how a Linux system boots, you can start to see how you can potentially do some cool things with it. In the last presentation, Brent was talking about iSCSI and whatnot. It's possible with Linux to boot over iSCSI without using any kind of local disk, any kind of local storage, which is kind of cool. I don't have that one as a demo today though, so I won't show you how to do that. But if we get time at the end, I can probably go into depth on some explanation of that. Yes. So I am in general staying high level. When it comes to the demo stuff that I'm going to be doing, that is x86 specific. But even with ARM or Power or take your pick of random architecture, they follow a lot of the same basic pattern. And so hopefully the concepts that I teach you'll be able to apply to all. Yeah. Yes. So the question was if they're with the iSCSI booting, if there was a way to make it selectable. The answer is yes. You can do it one of multiple ways, and that is a really interesting topic that I have done a bit of exploration in, but I don't have in the talk. So if we get time at the end, I can go over those. And something tells me we might have time. I mean, this is actually based on a presentation I gave many years ago at a previous job that only took like 25 minutes, so maybe this will go fast and we'll have time for those. So maybe not, I don't know. I have reworked it a bit. And then of course, because why not? We're geeks. We like to understand how things work. So that's another reason why you should care. This is an interesting diagram that I found years ago. I had a link for where I got it from that is no longer valid, so I had to go hunting for a new one. And yeah, it's on this Gizmodo article too. What this is a line showing the flow of execution of the Linux kernel as it boots. And so way up here is where essentially the kernel main gets called, or what leads into the kernel main getting called. And it has a single line that kind of swirls around up top, and then it gets to this giant mess down here. And there's just calls all over the place into different systems and whatnot that happen. You don't have to understand all what goes on there, but it's just kind of a cool image that shows there can be a lot of complexity in this, but we're going to distill it down to just the high-level stuff. And so here's a little diagram that I made that shows what I would consider the 4 high-level steps that a system goes through, and you'll be able to find at least small bits of this on just about any architecture that you go to. You're going to start off with your platform initialization, and this is what the very first bits of code that your processor is going to execute once it's received power. On an x86 system, this is going to be I don't want to get too much into that. I have a slide for that. After your platform initializes, you're then going to pass control over to your bootloader, and this is where you're going to have some kind of option as to what you're going to boot, what the system is going to do. And then afterwards, after the bootloader, we're going to get into the kernel. This is where Linux actually gets loaded and executed. And then finally, the kernel is going to start init, or PID1. This is what takes care of all of the user space applications on the system. It takes, once the kernel is done, only the kernel is running. It's got to somehow kick off, usable applications. And this is init, or the kernel calls init, and init takes care of making everything else available. So to start off with platform initialization. In the x86 world, this has traditionally been BIOS, or the basic input-output system. This is a wonderful friend that has been around for decades, but is now dying a ugly death. There are equivalents on other architectures as well, with varieties of names, but really what this thing, or what this bit of code is supposed to do, or this part of the initialization, is just take care of your very low-level stuff so that the system can then determine what it needs to do next. It will do things like initialize your memory controller. These days, you can't just start talking to your memory right off the bat. You've got to do several instructions that configure the parameters for the memory controller so that you can actually access your full range of memory. The other thing is, sometimes you'll want to have basic things like a keyboard input, or being able to talk on a serial port, or being able to display something on the screen as your system is booting up. Your platform initialization is what takes care of these kind of things. It can also, depending on different things, or give access to storage or network resources, usually through things like option ROMs. And so, like your different controllers could have a ROM on them as well. Where they provide access to different things. And so the BIOS might enumerate those, initialize those to give you additional accesses. Sometimes those things though are built into just your BIOS natively. Your BIOS is, at least what you'll find on just about all x86 systems today, is something that's written in assembly. They're closed source. Pretty much every vendor uses one of a few select options. With so the most common ones, Award, AMI, and Phoenix. There are others, but there are a couple notable exceptions to this that are open source and whatnot. Core Boot and CBIOS. Actually, has anyone here used a Chromebook? We got one, two. So Google has actually been pushing for using Core Boot on their Chromebook devices or the Chrome boxes, whatever. And so if you get one of those, you usually don't have a traditional BIOS. You have a Core Boot thing, and so and Google's actually been somewhat good about pushing their code changes for that into the upstream repo, and so you can actually get the code for your low-level firmware. Yeah. Mm-hmm. Yeah. The motherboard manufacturer actually buys licenses from those vendors, and their implementations are actually pretty modular. If you want to go digging in some of the nether parts of the internet, you can find the leaked versions of the tools that these vendors have for customizing the BIOS, and you can actually break down and see which modules are in the BIOS that your motherboard manufacturer provides, or your platform manufacturer. So another thing that sometimes gets thrown into that too is, I don't know what the acronym stands for, but SLIC from Microsoft. If you've ever bought a OEM, like say a Dell or HP, whatever box that came with Windows on it, and not had to worry about Windows activation, it's because what they've done is they've thrown a platform certificate from Microsoft into these things, and Windows then queries that during boot up to validate the licensing. So I won't get into what potential possibilities there might be for doing interesting things with that, because I'm not trying to get sued. So anyways, so after this stuff runs, you have your basic hardware initialized so that you can then do more advanced things. You then need to hand off control to a bootloader, and there are a couple ways in which the BIOS, in this case, will find a bootloader and execute it. The most common one is good old MBR. I'm guessing most in this room have dealt with partition tables and MBR at one point. But in addition to storing your partition table, it also has a code block. You get about 440 some odd bytes to store actual code. And so after the BIOS initializes, it will read this, the memory off here and execute the code there. 440 some odd bytes hasn't been enough for this in a long time. And so what modern bootloaders usually do is they'll write just a little shim that fits inside there that then finds code somewhere else on disk, and then it will read that code and execute that. Yeah. Yes. So GPT is a extended form of, or a different partition table layout. It actually leaves room for this at the beginning. Usually booting with GPT involves not using BIOS. It involves using EFI or UEFI, which I will get to at the end. So I have slides later on for that. So the other traditional, or I shouldn't say another traditional way of passing control from your BIOS to a bootloader is with with Pixie. This is network booting. And so what happens here is you'll have a option ROM on your on your system in some place, and it will go through a specified order of things to try to figure out what it should boot. Specifically, it's going to ask for a DHCP address. The DHCP server will return several options to it, and most built-in Pixie clients just know how to handle next server and file name. After it receives those options, it will then connect to a TFTP server at the next server that it receives and download the file name that is specified and then execute that. Pixie Linux is a very common one. iPixie as well as for what it will do next. And so the Pixie client will just download this code and start executing it. And that's where we'll use that for its next level in the boot process. Which gets us to the bootloaders. There's a wide variety of bootloaders out there. GRUB, Lovell, SysLinux, U-Boot, iPixie, Boot Manager. Which one of these is different? Most people wouldn't put Boot Manager in here because that's the Microsoft bootloader that's used for Windows Vista and later. I haven't actually gotten it working myself, but I have found documentation online for actually how to chain load GRUB from the Windows Boot Manager. So you could use it to eventually get to Linux as well. What this is, or what responsibility this has, is to find where your kernel is, load it into memory, and then execute it. These usually get they're usually very specialized for the environment that they're in. It can be very different based on desktop systems or going to embedded systems. For example, in this list, U-Boot is traditionally used in embedded systems, stuff like MIPS and ARM, though it does have an x86 port as well. And they can be very simple or very advanced, from scripting abilities to network access to even rewriting your operating system. Have any of you tried to modify a home router? Okay, I'm getting a few nods in here. Some of those actually have the ability in the bootloader. If you can talk to the bootloader through, say, a serial port or other method, you can tell the bootloader, download this image from this server and write it to your flash. So that you can actually overwrite your OS from your bootloader. So, or load a operating system from a different place. Let's see. I am going to hop over real quick. I meant to show a little bit of what you would see during the platform init, but I skipped that. So let me pop over to a terminal here. So I have a terminal here, which I have a QEMU command alias, or something that I can run here. I use QEMU a lot for my systems level things, combined with KVM. So this command is just going to start up a virtual machine for me. And so if I run this, and I'm going to give it, actually, let's do it without any drive. And hopefully we see here, hopefully you can see what's going on here. And actually stop. I don't think I can. Yeah, I don't think it lets me resize really to make it bigger. So sorry about that. And actually I have just paused the virtual machine as well. And you can see up at the top here where it started CBIOS, which is one of the open source BIOS implementations I mentioned. That's what it uses for its BIOS level in this. And then you saw there's this iPixie line right here, and that was where it initialized an option ROM, because it our QEMU includes iPixie with it for the network cards that it supports. So there it initialized that option ROM. And then it tried booting from several things. You can see it tried booting from a hard disk, couldn't read it. Tried booting from floppy, couldn't read one, or CD-ROM. And then it got into here, and it got into trying to do Pixie. And if I were to just let this run, it would try to boot something that would fail because I have things set up for later in the demo. But you can see what goes on in there. So that was to just kind of show platform initialization and how your low-level platform will try to find what it needs to hand off control to. Now let me connect a disk to this. So you can see this one, it immediately found something. Actually, let me go into this. No. Alright, so here, classic GRUB. You can see where this, this is what you would see on, or it's something similar. This is what you would see whenever you're booting a Linux system. In this case, I just installed Debian in this, and so they didn't add too much graphical stuff to GRUB, but on some other distros you'll get all kinds of graphical things in here. And I'm going to go ahead and hit E in here so we can see what kind of configuration things are in there, and that is kind of small up there. It looks just fine here on the confidence monitor. Oh, hey. There we go. Let's do that. So in here you can see there are multiple things that GRUB is or multiple directives that GRUB is configured for. It loads a few modules. For example, here it loads gzip.io. So usually your kernel is compressed, and so GRUB needs to be able to support decompression. Needs to load the information about how to handle MS-DOS style partitions. In many bootloaders, you'll see references to MS-DOS, which usually means MBR as well. So it needs to be able to read an ext file system. Then we set what our root hard drive is, or I guess the root partition that we're going to be reading from. And this is how GRUB 2 refers to things. GRUB Legacy had a slightly different method of referring to your hard drives and your partitions. But in this case, it's going to look at hard drive 0, which is your first hard disk, and then MS-DOS 1, which is your first partition. So we've got a little bit of discontinuity on partition, or on numbering, 0 indexed versus 1 indexed. But anyways, here it's going to search for this line is in case your hard drive ordering changes. So this directive tells GRUB to search through your devices for this UUID, which you can actually see it referenced down here as well. This is the UUID for my root file system. And if it finds a device with that UUID, set that as the root variable. So this protects the system in case you go through and change around the multiple hard drives in your system. GRUB can still figure out, oh, it's changed. Then it's going to load Linux, and I'll get into what this means later. And it's also going to load an initial RAM disk, and I'll get into that a little, or the difference there a little later as well. Let me go ahead and close this now and change. I'm going to tell this system to boot from the network this time. Let me have it start stopped so that I can make it bigger before we get into things. Control plus together. Continue. So here I told to boot from the network first, and what happened was It used iPixie as its Pixie client, which you can also use iPixie as a bootloader, which, yeah, if we get time, we'll talk into later. You can then see where it did a DHCP request right here. It got a address back. It also got a next server and a file name. So it then tried to TFTP from that server that file name, and it got it. And Pixie printed out a few additional things, and oh, actually, wait, no, this stuff is actually probably coming from Pixie Linux. So at this location, I have Pixie Linux. It printed some information about itself, and then it tried to load a configuration file, and in which case it just tried to load from the TFTP server its default configuration. And my configuration in this case, and make that a little bigger again. This is the configuration file I have in this case. I tell it just have a timeout of 5 seconds, which default I should do. The prompt says to give me the prompt to let me do something, and then I have 2 boot options. The first one says to load a kernel and RAM or kernel from this location and append these additional arguments to it. The initRD gets interpreted as well to load an initial RAM disk from there. The other option I have is to local boot, in which case Pixie Linux will just exit and return control back to the BIOS for it to go through its next boot implementations. So these are what, I guess, some examples of bootloaders, and you can see where your configuration options are in them. And on this one, I'll just go ahead and do this. If I do local boot, it just went to GRUB. So let's go ahead and stop that. Alright, back to these. So next, we just talked or showed some bootloaders in their configuration and what they do, and really what they're meant to do is just load the kernel and so that it can go through and do its thing. And what it will do, it will go through and reinitialize a bunch of things and then initialize itself. It's going to reinitialize hardware using its own drivers. The hardware drivers that are included in the low level are usually pretty simple and not that fast. Yes, question? So the question was, where in the kernel does it begin execution? Where in the kernel binary? So in this case, it is a ELF binary. So the executable linkable format, I think is what that stands for. And it's not just byte 0. It's there's headers in there, and it's still got its code and text segments. Well, the bootloader does. Correct. And so, I mean, the processor just executing codes. So the bootloader, which is the program it's running, understands ELF and can load that, the kernel into memory as another program, and then pass execution to it. And if you go looking in the kernel source, there is a main for the kernel, which is just something that it doesn't return from, really. So, and yeah, it's just a giant C program that allows execution of other things. So I don't want to say it goes to memory address X because one, I don't know, and two, it's probably not right. Yeah. So it's so it's going to go through and reinitialize your hardware usually using its own drivers for multiple reasons. It will reclaim resources from the platform. EFI is one that it will make a call in the EFI case. It will make a call over to EFI saying, "Hey, I don't need you anymore. Free up whatever you can." So it also needs to be told where its file system is. Where the rest of the system that it needs to boot lives at. There are multiple ways of specifying this, but it's handled using the root command line option usually. There are ways to get around this that are in modern systems. But you can give it just a block device, or depending on whether or not you have additional things around, you could give it a label to then give it for what the file system label that it should mount is, and or a UUID. Both those two latter ones do require UDEV having run so that it can properly set up links based on these names. So those require more advanced systems or auxiliary software to set that up for the kernel to use it. And it may need kernel modules to access devices before any file system is available. So if you've ever dealt with kernel modules, sometimes you need to load them from disk. Well, at this point in the process, though, you may not have access to the disk because you haven't loaded the modules. So a nice little catch-22 there, which is what the initRD or initramfs is supposed to fix. And this is just a really small in-memory file system that's loaded by the bootloader into memory with the kernel that holds a small set of kernels and or utilities to facilitate mounting the root file system. For example, AHCI, the HCI driver, and UDEV. And we use these to mount the root file system, and you can actually have a whole operating system inside the initRD or initramfs and skip mounting a file system. And this is an easy way to just run a system entirely in memory. So if you have a small image that you don't care about persistent storage with, you can do this and then just throw it away on the reboot. Yes? So the question is that how gparted or other live systems use to make sure that they're operating in the case where they don't have persistent storage or a disk. Yes and no. The majority of your live systems will use some form of a loopback device or the CD itself as a file system, and will mount that as their root, and then do some kind of copy on write file system that mounts on top of that for the writable aspects, and those writes will go into the memory and not onto disk and get thrown away at the end. I don't know of many systems that actually fully boot out of the initramfs and don't do anything else. It is possible I have done it, but it's not usually a practical thing to do. So, anyways, yeah, with the live CDs, they'll usually have several hundred megabytes of data on the CD, but they don't want to make the assumption that they can run on a system with multiple hundred megabytes of RAM. So they leave a lot of it on the CD and read that as needed. So, the difference between these two, an initRD is an initial RAM disk. This is the older style. It's not really used anymore. What this would be is you'll take a small, say 2-4 megabyte virtual block device that's mounted through loopback. Then you'll actually create an ext file system on that, put your files into that. And so when the kernel boots, it has that same thing going. And so it's got a virtual disk in memory as well as its own page cache. And so you potentially have each of your files in memory twice for that. And so that's where initramfs came in, the initial RAM file system. This just uses the Linux page cache as your file system. So it is an in-memory thing. It will read a CPIO archive and extract all the contents of that into this virtual file system, which is always dirty, so it's always in memory. It's not. It doesn't have a backing device behind it. So this is what is used now for most things. And so, like if you're on your system and you find your init RD, init ramfs, they mix the names up a bit, but you can just un-gzip it and then feed it through CPIO and get the contents of what is in there. Alright, and then we get to init. This is the first process that the kernel runs, and it's responsible for making the system usable for other applications. So things like your syslog daemon, your network interfaces, or network manager on a lot of modern systems like laptops and whatnot. Your X server, or your login prompts on your various terminals, VTYs. All of those get started by init and are handled by that. It's traditionally been the System 5 init that has been used, but it's somewhat limited. It's just a simple order-based system that it will start one service and then the next and then the next. And so, but with modern systems, there are lots of things that have dependencies on each other. And so you have crazy things like people writing shell scripts that just have a sleep in them during their init script to wait for something else to boot or something like that. And so in the past few years, there have been several replacements written. Upstart, Systemd, OpenRC are the most, or at least the ones that have gotten the most headlines recently. And yeah, they're also the most popular. Which now gets into, I'll briefly go into the Debian init debate of 2014. How many of you, are there any people in here that follow Debian closely, or that use Debian, or that know much about what was going on here? Okay, so Debian is the base distro that many things come from, including Ubuntu. And there was the question posed earlier this year. Well, it was decided that the System 5 init package needs to be replaced with something more modern. So the question turned into, well, which system do we go to? Canonical has been using Upstart in Ubuntu, and you could say it kind of fits with the Debian mentality a little bit more. It has a declarative dependency resolution, so a package maintainer will declare that an init script depends on these additional services at boot time, and Upstart will figure out those dependencies and boot things in the right order. One of the debates that kept coming up was they were saying, well, Upstart is portable to other kernels because Debian supports booting with a herd kernel or a FreeBSD kernel instead of Linux. And they were saying, well, we potentially could port this to other kernels, but it does not currently have that support. So that's why it's potentially. Then you have Systemd, which was started by some Red Hat employees. It has an implicit dependency resolution. So if you modify your applications to boot using its socket activation, Systemd can actually just start everything at once, and it will handle the communication between services. And so, say you have something that depends on syslog, but syslog hasn't started yet, the application can still connect to the socket for syslog because Upstart has opened to that socket, and when it detects a connect on that, it will start syslog and then hand the connection over to the syslog data. So that removes the necessity for package developers and whatnot to declare, these things depend on each other. But there is no hope for supporting other kernels in the upstream. There was a very heated debate because there are some very smart and also passionate people on both sides of that debate, and it was a debate that took the Debian technical committee a while to work through. I can't think of many other cases where they had this heated of a debate that took as long as this one did. And eventually they chose System D. And then afterwards, Canonical said, okay, well, we'll use System D for Ubuntu in the future now. And so the 14.10 release already has packages available for System D, but they're so early on in the release cycle for that, I wouldn't recommend trying it yet. Alright, so talked briefly, or went all the way through that. Now to talk briefly about how our platforms are changing on the low level for x86 systems. And this is also, to some extent, going to be, impacts ARM as well. BIOS is old and crusty and hard to maintain. It could use a replacement. And so now we have the Unified Extensible Firmware Interface. Started off as just Extensible Firmware Interface. This was a specification from Intel, originally written for the Itanium back in the 90s. It's actually been available for x86 systems since early 2000s. If any of you guys know Intel chipsets at all, I believe the i820 supported using UEFI, but just no motherboard manufacturers implemented it. So everyone was still using BIOS. It's written mainly in C, which is kind of nice. With BIOS, you're running in real mode all the way through until you get to your bootloader, and probably even until your kernel. With UEFI, the system changes to virtual mode very early on in the boot process, so your memory access is a lot more protected. It is also very huge. I don't have a source for this, but I did hear once that the source code for the reference implementation of UEFI is actually larger than the Linux kernel itself. So you have a kernel in your platform. So most implementations are based on the open source reference implementation, which is called Tiano Core. And all those manufacturers for BIOS, they all have UEFI versions that are pretty much all based on Tiano. I can't think of any that are not based on it. It's BSD and Eclipse licenses, and so unfortunately there's no requirement on your platform vendor's part to divulge the source. Sorry. And also some of the very early platform initialization is still closed source. An example of this, have you guys heard of the Intel Minnow board, which is a small embedded device that's supposed to be fully open source? You can get all the specs to build one yourself online. The one thing they don't include is the very early platform initialization. So the stuff that actually takes care of like the memory controllers and whatnot. So you still have to sign an NDA to get that little bit of code. So it supports GPT and booting from a volume larger than 2 terabytes. And this was probably the thing that really got motherboard manufacturers to transition to UEFI on their firmwares is hard disk for getting bigger. So we started to get larger than 2 terabyte drives, which MBR has a limit of no partition can go past the 2 terabyte mark. So GPT gets around that. It allows for much larger partitions, a lot more. You can have up to 128 partitions instead of 4. And so it does offer many advantages over MBR. But it also doesn't have the little code block to execute code. So for your bootloader, you actually have what's called the UEFI system partition at the very beginning of your disk. Well, it can be anywhere on your disk, but usually it's the very beginning. It's usually something like 1 to 200 megabytes. It's formatted with FAT, and it contains several files that are, applications that it can use as bootloaders. And it can have more than one. Then what you have is you can then put inside of your UEFI variables a boot option saying use this file system and this file on that file system, and then these arguments to use as a boot loader. And so on these, there's usually some key command you can hit during the boot sequence to get a boot menu in your UEFI. And after you've installed a system, both Windows and Linux or others that support UEFI, if you go into that boot menu, you'll actually see a boot option that says, Windows or Debian or Ubuntu, whatever, because it is able to specifically say this system is at this location, go for it. So that was something that wasn't possible really with BIOS. And just a little bit about Secure Boot, because this frequently comes up when talking about UEFI. There was this whole scare about Secure Boot a while ago. Basically what it is it's a way to trust that the code that your system is executing is trusted by someone. Who is that? What is trusted? Well, that gets into policy decisions, and policy is what caused the big stir a year or so ago in relation to Secure Boot. Microsoft required that Secure Boot be enabled on systems that were part of the Windows 8 logo process. So if you were a PC manufacturer and you wanted to put the Windows 8 sticker on your computer somewhere, you had to go through the Windows 8 logo qualification, which they required you to enable Secure Boot by default. They originally weren't going to. They were originally not going to allow it to be turned off, in which case you can only boot with an operating system that is trusted. And so then the question is, well, who's trusted? The only thing that you're pretty much guaranteed to have trusted is the Microsoft key, because that's what platform vendors are going to be including. And so the question is, how do we get Linux systems to do that? There was some very smart people who worked on that problem. If you get a distribution that was released anytime within the last year or so, it'll most likely just work out of the box on a Secure Boot system. Though you might find some exceptions. I know all the big ones support it perfectly now. And a big thing too is it's not DRM. It cannot be used as a DRM method. So don't think that that's something that it can be used for. If you have control over the variables that are used for deciding what code is trusted and whatnot, you can actually use it yourself as a great way of controlling what software runs on your system. I wouldn't be surprised if, in the not too distant future, if enterprise systems start providing ways for system administrators to define those keys so that they can make sure that nothing infects their systems from a boot level, or from a platform level. So, anyways, that actually went a lot longer than I thought. I don't have much. I did have lots of demo stuff to show, but don't have really much time to show them. Any questions at this point? Yes. So the question is, how did the Secure Boot thing get fixed? Basically, both Red Hat and then also the Linux Foundation got another bootloader, or they wrote another one that's just a very small kind of shim that they had Microsoft assign the signatures for. So it is trusted by the Microsoft key. And then from that little shim, they can then store keys of their own. So basically what it is that little shim will get executed. It will verify the other things against the keys that it knows and continue booting that way. It should work on pretty much any system that you have with Secure Boot. Hopefully Microsoft never revokes those keys, but it is possible that they could, which has caused a whole other stir inside the Linux community of whether or not we can allow runtime loadable modules in the Linux kernel that are not signed. Because if you can load a kernel module, you can write directly to hardware, or you can talk directly to hardware. And if you can talk directly to hardware, you can do funky things to affect the system in the future on future boots. So, Matthew Garrett, the guy who's been very vocal about this, is saying you can't allow unsigned modules or things like kexec, because that can be used to subvert secure boot. And if we let people subvert secure boot, Microsoft might revoke our key. Oh yeah. And I'll try to get these onto the conference stuff. So anyways, I do want to show real quick. I mean, I'm guessing most of you have probably booted a system with BIOS and MBR and whatnot. I do want to show real quick what an EFI looks like. So here is, oh, dang it. So I'm hitting F2 in here. So OVMF is a way to run the reference Tiana core inside of QEMU. So I hit F2 to go into the boot menu of the firmware, and you can see there's this boot manager option. So I'm going to go in here. And you can see it actually says right there to boot Debian. I also have another boot manager in here. You can boot to other devices. There is a default path that if you don't have any variables set up for a particular thing to boot in EFI, that it will try. But another cool thing is there's also a shell that you can get for EFI. Not all motherboard or firmware manufacturers include the shell in their firmware. This one does. And you can actually, it feels kind of like DOS, but you can do different things with it. So like I can do directory listings and browse around my file system. So if I look in my EFI directory, which I don't know if you guys can't really see that blue, but right here it says Debian and refined and then tools. So inside this Debian directory, there's GRUB. So GRUB is just an EFI application in this case, which it will then load. The other thing that you can do is there was support added to the Linux kernel recently to just execute the kernel directly as an EFI application. So if I do this, so you can see right here I have a kernel here, and if I do initRD equals -0.bpo.64, then root. Oh no, it's actually equals label equals fs. Hopefully that works. It just directly loaded my kernel and boots my system. So you could actually get around having another stage of something in there and just directly have your kernel loaded by your EFI platform. So like you could also, I don't think any distros actually can do this, but you could have it set up so that whenever you install a new kernel, you actually go through and just write your EFI variables for that boot option. So. I wouldn't say you cannot. I would say it's not near as reliable as it was in the MBR world. I have tried chain loading the Windows EFI boot manager from GRUB in EFI mode, and I have had it work, and I've also had it not work. So I wouldn't say it's not possible, but I wouldn't rely on it. So, but actually, my laptop right here, it has an EFI, and I do EFI booting on it. And let me go over here real quick. UEFI boot manager is a Linux command you can use to see what your system is currently configured as its boot options. And wow, I have a whole lot of them on here. But you can see down here I have Windows Boot Manager and Ubuntu. And the Ubuntu one loads GRUB, which then does chain the Windows one properly. So, I'm not quite sure why they were saying you can't. But like I said, I have seen it not work as well too, so I wouldn't say it's entirely reliable. Yeah, it's probably just an experience thing, and it didn't support it initially all that well, so it might also be old information on their wiki. So, but it does work okay now. Any other questions? I do have, just as a little bit of fun. Oh, dang it. A little bit of funny in there. I had this, but I actually had questions asked, so it wasn't just dead air at the end. So, alright, well, thanks for coming, and hope you learned something.